Recursion in computer science is a method where the solution to a problem depends on solutions to smaller instances of the same problem. The approach can be applied to many types of problems, and recursion is one of the central ideas of computer science. The power of recursion evidently lies in the possibility of defining an infinite set of objects by a finite statement. In the same manner, an infinite number of computations can be described by a finite recursive program. Even if this program contains no explicit repetitions, most computer programming languages support recursion by allowing a function to call itself within the program text. Some functional programming languages do not define any looping constructs but rely solely on recursion to repeatedly call code. Computability theory proves that these recursive-only languages are Turing-complete. They are as computationally powerful as Turing-complete imperative languages, meaning they can solve the same kinds of problems as imperative languages even without iterative control structures such as while and for. Recursive functions and algorithms. A common computer programming tactic is to divide a problem into subproblems of the same type as the original, solve those subproblems, and combine the results. This is often referred to as the divide-and-conquer method, when combined with a lookup table that stores the results of solving subproblems. It can be referred to as dynamic programming or memoization. A recursive function definition has one or more base cases, meaning input for which the function produces a result trivially, and one or more recursive cases, meaning input for which the program recurs. For example, the factorial function can be defined recursively by the equations 0 equals 1 and for all n greater than 0 equals n. Neither equation by itself constitutes a complete definition. The first is the base case, and the second is the recursive case. Because the base case breaks the chain of recursion, it is sometimes also called the terminating case. The job of the recursive cases can be seen as breaking down complex inputs into simpler ones. In a properly designed recursive function, with each recursive call, the input problem must be simplified in such a way that eventually the base case must be reached. Neglecting to write a base case, or testing for it incorrectly, can cause an infinite loop. For some functions there is not an obvious base case implied by the input data. For these one may add a parameter to provide a stopping criterion that establishes the base case. Such an example is more naturally treated by co-recursion, where successive terms in the output are the partial sums. This can be converted to a recursion by using the indexing parameter to say, compute the nth term. Recursive data types. Many computer programs must process or generate an arbitrarily large quantity of data. Recursion is one technique for representing data whose exact size the programmer does not know. The programmer can specify this data with a self-referential definition. There are two types of self-referential definitions: inductive and co-inductive definitions. Inductively defined data. An inductively defined recursive data definition is one that specifies how to construct instances of the data. For example, linked lists can be defined inductively. Data list of strings equals empty list. Const string list of strings. The code above specifies a list of strings to be either empty, or a structure that contains a string and a list of strings. The self-reference in the definition permits the construction of lists of any number of strings. Another example of inductive definition is the natural numbers. A natural number is either 1 or n plus 1, where n is a natural number. Similarly, recursive definitions are often used to model the structure of expressions and statements in programming languages. Language designers often express grammars in a syntax such as Bacchus NAUR form. Here is such a grammar. For a simple language of arithmetic expressions with multiplication and addition, less than expr greater than, equals less than number greater than. This says that an expression is either a number, a product of two expressions, or a sum of two expressions. by recursively referring to expressions in the second and third lines. The grammar permits arbitrarily complex arithmetic expressions such as +8, with more than one product or sum operation in a single expression. Co-inductively defined data and co-recursion. A co-inductive data definition is one that specifies the operations that may be performed on a piece of data. Typically, self-referential co-inductive definitions are used for data structures of infinite size. A co-inductive definition of infinite streams of strings, given informally, might look like this. A stream of strings is an object S such that head is a string, and tail is a stream of strings. This is very similar to an inductive definition of lists of strings. The difference is that this definition specifies how to access the contents of the data structure, namely, via the accessor functions head and tail, and what those contents may be, whereas the inductive definition specifies how to create the structure and what it may be created from. Co-recursion is related to co-induction, and can be used to compute particular instances of infinite objects. As a programming technique, it is used most often in the context of lazy programming languages, and can be preferable to recursion when the desired size or precision of a program's output is unknown. In such cases, the program requires both a definition for an infinitely large result, and a mechanism for taking a finite portion of that result. The problem of computing the first n prime numbers is one that can be solved with a co-recursive program. Types of recursion: single recursion and multiple recursion. Recursion that only contains a single self-reference is known as single recursion, while recursion that contains multiple self-references is known as multiple recursion. Standard examples of single recursion include list traversal, such as in a linear search, or computing the factorial function, while standard examples of multiple recursion include tree traversal, such as in a depth-first search, or computing the Fibonacci sequence. Single recursion is often much more efficient than multiple recursion, and can generally be replaced by an iterative computation, running in linear time and requiring constant space. Multiple recursion, by contrast, may require exponential time and space, and is more fundamentally recursive, not being able to be replaced by iteration without an explicit stack. Multiple recursion can sometimes be converted to single recursion. For example, while computing the Fibonacci sequence naively as multiple iteration, as each value requires two previous values, it can be computed by single recursion by passing two successive values as parameters. This is more naturally framed as co-recursion, building up from the initial values, tracking at each step two successive values. See co-recursion. Examples. A more sophisticated example is using a threaded binary tree, which allows iterative tree traversal, rather than multiple recursion. Indirect recursion. Most basic examples of recursion, and most of the examples presented here, demonstrate direct recursion, in which a function calls itself. Indirect recursion occurs when a function is called not by itself but by another function that it called. For example, if f calls f, that is direct recursion, but if f calls g which calls f, then that is indirect recursion of f. Chains of three or more functions are possible. For example, function 1 calls function 2 calls function 3, and function 3 calls function 1 again. Indirect recursion is also called mutual recursion, which is a more symmetric term, though this is simply a difference of emphasis, not a different notion. That is, if f calls g and then g calls f, which in turn calls g again, from the point of view of f alone, f is indirectly recursing, while from the point of view of g alone, it is indirectly recursing, while from the point of view of both, f and g are mutually recursing on each other. Similarly, a set of three or more functions that call each other can be called a set of mutually recursive functions. Anonymous recursion. Recursion is usually done by explicitly calling a function by name. However, recursion can also be done via implicitly calling a function based on the current context. which is particularly useful for anonymous functions, and is known as anonymous recursion. Structural versus generative recursion. Some authors classify recursion as either structural or generative. The distinction is related to where a recursive procedure gets the data that it works on, and how it processes that data. Functions that consume structured data typically decompose their arguments into their immediate structural components and then process those components. If one of the immediate components belongs to the same class of data as the input, the function is recursive. For that reason, we refer to these functions as recursive functions. Thus, the defining characteristic of a structurally recursive function is that the argument to each recursive call is the content of a field of the original input. Structural recursion includes nearly all tree traversals, including XML processing, binary tree creation and search, etc. By considering the algebraic structure of the natural numbers, functions such as factorial may also be regarded as structural recursion. Generative recursion is the alternative. Many well-known recursive algorithms generate an entirely new piece of data from the given data and recur on it. HTTP refers to this kind as generative recursion. Examples of generative recursion include GCD, quicksort, binary search, mergesort, Newton's method, fractals, and adaptive integration. This distinction is important in proving termination of a function. All structurally recursive functions on finite data structures can easily be shown to terminate via structural induction. Intuitively, each recursive call receives a smaller piece of input data until her base case is reached. Generatively recursive functions, in contrast, do not necessarily feed smaller input to their recursive calls, so proof of their termination is not necessarily as simple, and avoiding infinite loops requires greater care. These generatively recursive functions can often be interpreted as co-recursive functions. Each step generates the new data, such as successive approximation in Newton's method, and terminating this co-recursion requires that the data eventually satisfy some condition, which is not necessarily guaranteed. In terms of loop variance, structural recursion is when there is an obvious loop variant, namely size or complexity, which starts off finite and decreases at each recursive step. By contrast, generative recursion is when there is not such an obvious loop variant, and termination depends on a function, such as error of approximation, that does not necessarily decrease to zero, and thus termination is not guaranteed without further analysis.